Hello folks, so today we're going to be having a look and a deeper analysis at the new released 21700 based batteries for the Parkside 20 volt team, and also the smart charger that is part of this new ecosystem. So for the battery itself, we just have the 4 amp hour version at the moment. There should be a double stacked 8 amp hour one available very soon too. Nothing too surprising here. We have the Bluetooth connected battery that looks like this. Nothing too exciting or unexpected here. We have one simple button for the battery status, and this button also serves for the Bluetooth pairing. So holding down the button for I think 5 seconds activates the Bluetooth, holding it down for 10 seconds turns the Bluetooth off. So this gives you the option to pair it with the Little Home app. So when you have your battery set up, you can pair it inside the app. As you can see, I have 2 batteries and the charger inside the app here. So when I go into battery A in this case, I can see it here, so it gives me the status. If I want to make sure this is the correct battery, I can click battery identifier and it will blink the LEDs. The app at the moment isn't too informative. They also are updating some of the functions. I think these are mostly just bug fixes that are appearing here. The app just shows you the basic status of the battery. You can switch through some of these charging, discharging, and temperature graphs. Unfortunately, these aren't updated in real time. They only plot data if you're actually looking at the graph. So if you go out of the app, use the battery, and hope to come back here and see a nice plot of your battery usage, that unfortunately isn't going to work. Back here towards the bottom, we have some additional information and functions. We can switch the battery mode to different setting. This basically just gives you various permutations of the minimum discharge voltage where the battery is going to cut off, and the discharge current. This is all soft safety, so there aren't any MOSFETs or any switches in the battery itself. It'll just signal the tool through its T-pin that it is not okay, and it will shut the tool off, but the actual connections to the 20 volts will never be severed. It's the tool deciding to stop using the battery based on these parameters. Here we have some notification functions that it tells you if it's having any issues. At the bottom here we have this information page, which gives us the charge and discharge current and just a bit of stats on the battery. I've noticed that especially the discharge isn't very sensitive, so I had to find something that would have a high discharge rate sort of instantaneous just to get this graph to move. So I have the hot glue gun here. So if you watch the discharge current when I power it on, we'll see if it shows anything. Sometimes it's very laggy. Okay, so it's showing 1 amp being discharged now. It looks to be very insensitive to low amp discharge rates. So now it's already gone back to 0 since the core has heated. So even if I turn it back on, it's really not going to show anything. So the discharge current indicated here is a bit flaky, and it will only really show if you have some massive discharge. I tried it with the soldering iron too. You can initially get 1, 2, 3 amps showing here, but then when it's toward its steady state, once it's warmed up, for example, it really doesn't show anything. I guess with the power tools, you'd potentially see a higher indication, but as I said, you really have to have the app open all the time and be monitoring these values to see anything. It won't log any data itself. Here we have this line, device info, no smart device connected. This never gets populated even when connected to the charger. I was hoping that the charger, since the batteries only have Bluetooth, but the charger has both Bluetooth and Wi-Fi, that it would act as like an internet gateway to provide you the battery status data on your phone when you're outside Bluetooth range. But the charger and the battery never communicate with each other. The charger just delivers its charge and charge status information that it's able to detect and doesn't communicate with the battery. So maybe this is for some future usage, but I have no knowledge of that at this time. Statistics really doesn't show you anything, just how many cycles the battery's been through. Nothing too exciting. As I said, these graphs are kind of laggy while you're in the app. You can see that 1 amp little blip here. It'll show you something, but if you're outside of the app or using a different battery, it will not register. One other function that we have here is this, see, it's requesting an upgrade here, is this safety switch function. You should be a bit careful with that. That allows you to set a pin to the battery to lock it out. So if you go in here, you can set a 4-digit pin, confirm that, and then your battery is locked. But again, there's still 20 volts power at the power pins. It's just setting the T pin that's marked on the battery. You'd think that's a thermistor, but it's just a battery okay status. So when this pin is pulled to ground through anything, I've measured this between 3 kilo ohms and 30 kilo ohms, the tool thinks the battery is good to go. If this goes outside that range, usually it's just open circuit. When the battery is unhappy, either because it's interior thermistor is showing an overheat condition, or the current sense resistor has showed an overcurrent situation, it will actually set this T pin or battery status OK pin to not OK, and then the tool will shut itself off. But as I said, since there's no switching elements inside the battery, it really can't actually cut its power. So this, again, the security is very much a soft function. The only issue here is if you've forgotten your pin, and you don't know it anymore, I'm not sure the battery will lock itself at any point, but you will not be able to get this battery to work with the tool. It will still have 20 volts here, but since the T pin is communicating that the battery is not ready for use, no Parkside tool will take power from the battery. So I looked in the manual. There is a procedure to reset the pin, and this involves you going into the battery device information, looking up your virtual ID that corresponds to your battery, emailing, I think, Grizzly tool support, and then I guess through the Tuya app and through the internet they will unlock your battery. But that seems to me a very long-winded process that they've probably never done before. So don't lock your batteries out, because you'll have trouble getting them unlocked again. And especially if you're buying the used batteries, this might become an issue where the battery is locked and the process to unlock it is very ungainly. I don't think that the 10-second reset on the button actually resets the security, but I might be mistaken with that. So without further ado, let's take a quick look inside the battery. So by the magic of buying two, we can see what this battery looks like inside. So it has a different construction than the previous Parkside batteries. It has these two side panels, each with 4 screws, and then this top that goes on like that. But construction-wise, as we knew, we have the 21700s here. 5 batteries, 4,000 milliamp hours each. As far as the circuitry on top, we have our cell balancing transistors and resistors. Here we have our Bluetooth controller and communications board. We have our large MCU here. We have our battery connections here. We have our NTC thermistor here. Then we have our pins here. So we have our negative, our 20 volt positive, then our thermistor pin, battery OK status, and our ID pin that is used by the charger to determine the charge current. So this pin is only used by chargers. This pin, the thermistor pin, is only used by tools. So this tells the tool it's okay to use the battery. If the battery is unhappy with anything, it sets this pin to open. Otherwise, it's connected to ground by pretty much 10 kilo ohms of resistance. If it opens that circuit, then the tool won't want to use the battery. This is used with the overcurrent protection and the security functions. Also, we have a fuse that's built into this metal tab, and this also serves as the current sense resistor. They've obviously calibrated this element here. Since you can see, we have a connection on both sides of this fusible link or low value current sensing resistor. So reading the voltage across this element here, they're able to sense the current. If you remember the previous version, so this is the B2 version of the 18650 battery with the cell balancing. We can see the resistors here. They had an extra onboard fuse and current sense on the board. Here they've offset it to that top corner. So nothing too radical in the new battery. Of course, the new cell type, these two are equivalent, 4 amp hours each. They've obviously changed the MCU and a little bit of the design on the battery, but nothing too crazy going on here. So that is all really I need to say to this new battery. Let's go over and have a look at the charger. So this is the PLGS 2012A1 blah 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 Wi-Fi Bluetooth charger. I have it set up right here so we can bring that into frame. Nothing too radical here. We have just 2 buttons on the charger itself, an eco button for slow charging that should prolong your battery lifetime, and the 60% button that, according to the manual, is for long-term storage. So if you want to leave the battery in the shed over winter, you charge it to 60%, and that's good state of charge for long-term storage of lithium-ion batteries. So back to the app again. The charger communicates initially via Bluetooth to set up your Wi-Fi password, and then it communicates via Wi-Fi. So to set up both the battery and the charger in the little home app, you just go to the little plus in the corner. If there's a device pairing, I believe it'll pop up on this main screen, but otherwise you have to go into Others, and then you select Others 1 to sync the charger, or Others 2 to sync the battery. Others 3, I don't know what that is. That will be a mystery product for another day. But once you've set up the charger, and especially for the chargers, the batteries detect very quickly. The charger needed all of the 2-minute connection time that's shown in the app. So really be patient setting this up, and give it all the time it needs to sync up and, reset or plug in the charger. Since there's no buttons, this communications is just a light. So you just plug it in, go to connect through the app, and it will eventually find each other. So if we go into the smart charger in the app, we also get a bunch of information. We can change the charge mode, which basically just changes the maximum charge current. you can set the functions that you have here. Again, you can set some notifications. There's also some, oh no, there's no graphs on the charger. You can go into the details to either upgrade the firmware, again, up until now, just bug fixes, or just to check your device info. Nothing too exciting here. If we actually put a battery onto the charger, it should register that something's been connected. This battery's pretty much charged already. You can see the eco button is lit. I can hit the 60%. The fan comes on. Now it's charging in performance mode. There's this switch button here that you can click, and that stops the charging on the charger remotely. If you turn it back on, you can see it's trying to charge once more. I guess this might be useful in some rare instance. Nothing too exciting to be set or changed on here. I guess it would notify you by push notifications once the battery's charged. I guess this is interesting, but nothing really world-changing here. Again, as I said, it would have been nice if the charger actually interfaced locally with the Bluetooth of the batteries and then sent that information through the internet into the app. Then when you were outside the house, you could read the charge status of your batteries in the shed, for example, but they haven't done that. If we go into the charger, it does have some interesting design elements into it. So I'm just going to unplug this. I've gone as far as to remove some of the screws at the bottom. These large capacitors that are charged at rectified mains are obviously still on, so we're just going to spend a second for them to discharge before I get a good zap out of this. So there are 6 screws here, 4 of them covered by rubber feet that I've very kindly removed to save time. This bottom cover just pops off. There are the infos of that. This reveals the circuit board. This is usually held in by 3 screws here. So we have it unplugged. This are the mains caps. Let's just quickly, okay, that's fine. So here we have the circuit board. The cable is just retained here. There's a little fan in the back here. Then there's some connectors here for the charging port and the fan that we can remove. That removes this top part and the fan. Here we have our circuit board released from the case. Very nice and interesting design. Here we have our monolithic Wi-Fi and Bluetooth module. This is obviously the secondary side. This is the primary. We have 2 switch mode converters here. You'll see this one will be powering the electronics, the ICs on the secondary side. This is our main converter that's going to do the battery charging. Here we just have our input noise filtering, bridge rectifiers. There's 2 here just for heat dissipation purposes, some MTCs, our mains capacitors here with our 320 volts DC. Here we have our switching MOSFET covered with this silicon carni. We have 2 optocouplers down here that will be the voltage feedback. In the back here, you again can't really see them. We have 3 double diodes. You can see the 3 screws on back here that are doing the secondary rectification, and we have this big inductor here. So when we flip this board over, we can see that laid out here. So we have input filtering, rectifier, our 2 tracks going into our primary coil or winding on the transformer. Here we have a second winding, it seems, but this is actually false, since here we have a forward converter and a transformer and not a flyback power supply. We actually have our primary winding between these two pins, demagnetizing winding between pins 1 and 3, and then pin 4 is a ground with a shield winding inside the transformer that is not connected on the other end. So our switching is done by this chip here. This other small IC is doing the switching of this small switch mode power supply, which is a flyback. This is producing 10 volts as auxiliary power to power the ICs on the primary side, and 5 volts power here to power the secondary side ICs, with a 3.3 volt regulator here that's again powering everything. On this side here we have an LM358 that's doing the voltage feedback through these two optocouplers. We have our main MCU, we have our little Wi-Fi and Bluetooth board connected here. What's interesting here is the forward converter design. So you can see here we have our single winding on the secondary side, but we have 3 double diodes. 1 double diode on this end of that winding and another 2 double diodes on the other side, with this massive inductor that's connected here, also appearing here. And then we have our 3 pins that go to the connector to the charger, which is positive, ground, and ID pin, or no, sorry. Yeah, so positive, ground, and ID. So how this works, first I was thinking this is a very standard flyback supply, and I wasn't understanding these windings. I thought this was some kind of auxiliary winding, but this chip uses optocoupler secondary side feedback and not an auxiliary winding to set its voltage, so I was totally confused. And then I had these extra diodes on the secondary side, which wasn't making any sense. So here I just have a quick sort of sketch of the setup here. So as you can see, we have our primary winding, and then we have this weird rogue winding that I call it on the schematic, that was just connected to ground through this diode that's going the wrong way. And then here we have our shield winding that again is not connected to anything there. Then at the bottom we have our other switch mode, which is the small one providing the power, and then our secondary output. But it turns out after some head scratching that this is a forward converter, and this corresponds to the topology very nicely. We have our 2 diodes on the secondary side. We have our big inductor also on that side. We have our primary winding here with the transistor switching it in line. And then we have this other demagnetizing winding with this weird diode in series with it. So forward converter it is. Compared to a flyback, apparently a forward converter is a bit more efficient. So they've used it here just to be modern, let's say. So as you can see, it's a bit weird having these additional diodes on both ends of the winding. So the diodes are both pointing in to the center pin from the outer pin. So you have rectification going this way and rectification also going this way. So at first glance, it really doesn't make sense what kind of rectification was going on here. But after a bit of research, it all made total sense. These 4 MOSFETs here that are N-channel MOSFETs, 2 facing one direction, 2 facing the other. This is just to use the body diode in blocking mode here, and then just to dissipate energy and thermals, just splitting it up over the 4 MOSFETs. And these are exclusively used for current control, since you have the different modes, balance, performance, eco, for the charging. So by regulating their gates, I think they modulate the charge current that's being put into the battery. So as far as the current flow here, so when the primary winding and the MOSFET here that is switching it is closed, a current flows through the primary winding. Similar current flows through the secondary winding. So we have our positive end here. This is rectified by this diode here onto the positive rail, that's this copper area in the middle. This is allowed to flow through these activated MOSFETs to the positive pin, charging the battery. And then we have our return power flow that is going from our ground connector here pin. It flows through this wide trace here through this inductor to the negative end of the winding. But as you can see here, once current flow stops through the secondary winding, we have energy stored in our inductor. So this becomes positive, this is a negative. So current flows from the positive through these two diodes to be rectified to the positive rail, through the MOSFETs to the positive pin to charge the battery, returns through the negative pin here to the negative end of the inductor, which is negatively charged. So matching exactly the schematic that we have here. So I just wanted to add this little addendum and show you some scope captures of the signals being sent. As I mentioned before, on the battery we have 4 pins. The charger uses the ID pin, which happens to be the left pin just beside the positive contact. The tools, though, do not use this ID pin. They use the pin sometimes marked T on the tools. This would be the pin directly next to the negative contact here. And as I said before, the T pin is just a battery OK signal that's pulled to ground at around 10 kilo ohms to show the battery is in working order for the tool to use it. The security setting, any overcurrent, overtemp, just set that pin to open, and the tool stops using the battery even though the full battery voltage is still available on the positive and negative pins. So the ID pin here sends out serial communication that just identifies the battery capacity. So I've actually captured those signals coming off of this pin off to the side here, this rightmost pin, and you can see those 2 captures on the screen now. There's only 2 battery types or signals that I've detected, both the 4 amp hour 21700 base battery and the older 18650 4 amp hour battery have the same ID signal. The 2 amp hour battery has a different signal. I believe there was a different signal, of course, for the 3 amp hour version that I don't think ever actually was sold retail, and there will probably be a different signal to identify the 8 amp hour 21700 based battery that's coming out now. Another signal that we can get off this board is the Wi-Fi, Bluetooth, Zigbee integration board that's stuck on here. We can see the contacts of the board here. So first we have a ground, then we have VCC 3.3 volts, then we just have a pull-up resistor on this 3rd pin that is probably just an enable pin, and then we have just 2 more pins connecting to that board. This is the charger transmit, and this is the charger receive from the board. Both, as you can see on the scope captures, are just serial transmissions. I say this is a receive and transmit, some kind of UART based system, as the rightmost pin only shows activity when commands are input through the app to change the charger settings. All in all, a very nice design for the smart charger. Some very nice functions integrated. Nothing too special, again, nothing too crazy going on, but certainly a very good combination and upgrade for the future for the Parkside 20-volt team. The 8 amp hour battery that is the double stacked 21700 should be coming out in the next week, or at least I should be getting it then. It should be reaching the German little shop within the current month of January, I think. So stay tuned. I have a lot more content coming in this new year. So be sure to like and subscribe if you enjoyed this kind of video, and be sure to check in again. Thanks for watching, and see you next time. Bye-bye.